Now, I mentioned before that there is a page on a logarithms tutorial. Do you remember? You do? You don't look like you remember. I'm now formally assigning that page. Before I just told you about it, and you can start on it if you feel like it. But this time I'm formally assigning it because we're now deep into chapter 8, and we're going to be talking one day about decibels. Although the chapter in the book has left out that one paragraph that mentioned decibels, and I think at the time it was because it didn't have enough background. To understand that paragraph, you'd have to understand a lot of background. So rather than make the chapter bigger, and they cannot just expand textbooks endlessly, because the thicker the textbook, the less accessible it is. You've got too much stuff, and it's hard to finish. So it was simply removed. I'm guessing that's what happened. Because it was too much to explain, they just took that paragraph out. The paragraph is still on the web page. So if you look at that page on the website about the logarithms tutorial, you will find that that paragraph has been copied there. And it's on page 11. Phonetics 2, page 11. And that one has just one link, and that's to the tutorial. If you haven't done it yet, go ahead and do it. You will be surprised at how easy to understand it is, and it's actually fun, because he divides it up into 18 pages, and each one is one little step to understanding it better. And the way learning works best is if you do it in baby steps. One little step, 好像不很费力. Another baby step, 这个已经懂了，这个就不难了. And it goes like that, step after step. So after 18 steps, you think, logarithms aren't hard. 没什么. That's exactly what you'll feel. It happens every year. So one kind of inspiration you can get from it is pedagogy. Pedagogy, which means how we teach and how we learn. And you will find that anything that can be put in that form can probably be taught and learned quite easily. He's learned an excellent way of teaching. So those of you who are interested in teaching, well, all of us have to be interested in teaching and learning somehow or other. Pay special attention to how he does it, how he achieves that. Something that scares a lot of people, and then he finds a way to make it very accessible and easy and actually fun. Okay? And I already asked you, I asked you last time to put in a short essay about what we can do to improve learning in Taiwan and teaching. Remember? That was supposed to be part of your notes for today? Everybody remembered it? Okay, good. Just so it's there. And it's really important. I'm starting up a new list or a new page on Facebook, which is about education, about this topic. I've just started it. It's called A Fresh Start for Education in Taiwan. And we're going to start collecting materials on it, links, discussion. So just so you know about it, I'll send you a link if you're interested. Today we're going to concentrate on Chapter 8. We need to move ahead. And we're going to start talking about perturbation theory on page 192. And whose turn? Go ahead, Miranda.
Perturbation theory.
Okay, what is the stress?
Perturbation theory.
Right. I know it's often an afterthought, but you'll get better and better at this if you read ahead and you think ahead. Pre-reading is necessary. For a native speaker, even, it's necessary. We do it more naturally and we don't know the rules explicitly, but by reading it over, instead of saying, perturbation is a concept of, in that case, we could stress things quite differently. But as soon as we see theory, perturbation theory, we have to go down. Our brain will hear ourselves reading it. Everybody paying attention? When we're pre-reading, we're listening to ourselves read it. We don't have to even read it aloud. Our brain is reading it, just the way the echo method works. We've got that voice in our head. We read ahead, we hear our voice reading, and as soon as we come to theory, and if we start out perturbation theory, then we start over. That's what native speakers do. Now, 何况是 non-native speakers, you have to do it too. And I know this. Actually, it's not just me guessing and self-observation. I've mentioned that my father used to record books for the blind. He did it for like 30 years, since I was a really little kid. He worked downstairs, and I heard his voice coming through the heating system of our house, because we've got tubes from the basement going to all the rooms. I would hear my father's voice coming out of the tubes when he was recording these books for blind people. When he was reading, he would start reading a sentence, Suddenly he would stop, turn off the recorder, go back, read it again, because he forgot a compound stress or something like that. He had to go back and re-record. So I have actually firsthand experience with how native speakers pre-read or fail to pre-read or start reading and have to go back and fix something. From my father, who was extremely educated. He was a well-educated man. He knew like 5 languages. He read a lot. So from an educated native speaker, I was able to hear how we read just by listening to him record, which means that you as second language speakers of English, you need to pre-read. Remember that, pre-read, the importance of pre-reading. Text markup will help you. I do it before I record on Ivy a lot of the times. I just take a red pen, I mark where the pauses are. I mark where I have to remember to go up. I mark where I have to remember a compound stress. You guys should be taking notes. This is more important than it sounds. It sounds like 理所当然. Whenever I see students not taking notes, I conclude it's 2 things, one of 2 things. One is they think, this is a 老生常谈, everybody knows this, so we don't have to write it down. The other one is, I don't believe you. It's one of 2 things. This one is more important than you realize, the importance of pre-reading. You need to pre-read. Take a pencil, because I don't really like to make permanent marks in books. I use a pencil if I have to. You mark it in your book with a pencil, where you need to pause, watch out for certain stresses, intonations, etc. Please, I hope that's in your notes now and in your head. You need to pre-read. Otherwise, you're going to go, whoops. Otherwise, if the teacher doesn't mention anything, you keep going and then you forget to fix it in the future, right? Because most teachers, first of all, you don't read aloud in most classes. Is that right? And even if you read aloud, I don't think most teachers will stop you and tell you to fix things like this. Which means that from the few rules you're getting from classes like this, you have to do the rest yourself. Not wait for somebody to tell you. You have to be independent. You have to be very 主动 in your learning here. You can see right away this is a compound noun. So read ahead and find the other compound nouns, other things where you have to do special things. Let's go ahead.
We saw earlier
Let me hear the title again.
Perturbation theory.
There we go. Good.
We saw earlier with the formula F and N equals to 2
2 times
2
n
times n minus 1 times c divided by 4l.
All right, remember all the terms, right? Fn is one of 3 formants, 1, 2, or 3. Fn is F1, F2, or F3, one of those 3, but not F0. F0 does not count here. F0 is what? Fundamental frequency, and that's 铃铛别论. That's something totally different. Then we multiply the n, that means if it's 1, 2, or 3, by 2, and then we subtract 1 so that we get an odd number, multiplied by speed of sound, divided by 4 times the length of the vocal tract. Okay, go ahead.
That even a tube with a uniform diameter has simultaneous resonance frequencies.
Resonance frequencies. Okay, that's another example.
Several different pitches at the same time. Furthermore, these resonant frequencies change in
These resonance frequencies.
When
you read it the first time, I thought it was these resonant frequencies, which would be okay because then it would be a phrase, adjective plus noun. So your pronunciation, your stress is going to affect how your hearer hears things because the NCE and the NT are not necessarily that clear. These resonant frequencies, or these resonant frequencies, we use compound stress to understand things. It's not just a rule for no point. Okay?
Furthermore, these resonance frequencies change in predictable ways when the when the tube is squeezed at various locations.
You can say tube, but I don't. I say tube. As long as you're learning one accent, it's good to be consistent. You can put the tube in if you really want to some other time, but for the sake of learning one system consistently as possible, I recommend that you just follow what I do just to get one system very clear in your head. And I don't say various, it's various. Okay, the tube, go ahead. When the tube?
When the tube is squeezed at various locations.
Various.
various.
Yeah,
Various.
that's what I say.
Okay. This means that we can model the acoustics of vowels in terms of perturbations of the uniform tube.
Of the
Uniform tube.
tube. Right, and stress, because uniform here is not 制服. It's an adjective of the uniform tube.
Of the uniform.
Not duh.
Of the
Right.
uniform tube. For example, when the lips are rounded, the diameter of the vocal tract is smaller at the lips than at other locations in the vocal tract. With perturbation theory, we know the acoustic effect of
Effect, not a fact, effect. Effect, eh? Smile a little bit. Effect. Everybody, effect. Effect, watch. Effect.
The acoustic effect of constriction at the lips, so we can predict the formant.
不要重.
So we can predict the formant frequency differences between rounded and unrounded vowels.
Between what? Can anybody help? Remember contrast?
Rounded and unrounded vowels. Unrounded
There
vowels.
we go. Why? Do you know why?
The contrast.
Contrast and un is the new part. Everything else is the same. We contrast the new part. Did anybody understand a word of this? Okay. So we have our formula here and we know how that works. Even if a tube has a uniform diameter, let's understand that first. Remember when we looked at the exploratorium, we had bottlenecks, right? It was narrower in some parts and wider at other parts. This is saying even if we do not have that kind of a tube, we have a tube that is not narrowed at different parts, it's just a straight tube. 它的直径是均匀的，都没有变. So far so good? We still will have simultaneous resonance frequencies. That means even in this tube where there is no perturbation, that means there are no parts that are squeezed smaller. 我们根本没有变得比较窄的那几个地方，没有的情况之下，还是会有 F1, F2, F3 类似这样子的共鸣，有不同的共鸣。So remember we said that we have formants because of the differently shaped spaces in our vocal tract, right? 这个 space 有这样子的一个共鸣，这个 space 有这个几何的共鸣，两个接到这个气流，还有这些fundamental frequency plus overtones， 它就会挑出符合它自己的那个 natural resonating frequency， 然后会这样子，对不对？ Are we okay or not？ 不同空间的大小跟形状，它就会依照它自己的 natural resonating frequency 会加强某一些 overtones. Is that right? Now, in that mental picture we imagine different sized tubes, right? They've got like a narrow end and then a fat middle, right? 不同大小，而不是很均匀的一个管子。That's what we have in our mind. If you're all with me, then nod. If you're not with me, let me explain again. Not quite, Miranda?
Yes.
It's okay. I just need a little nod and I'll keep going. If I don't get a nod, then I'm going to think maybe you don't get something, I should explain it. Try to explain it again. Even if we do not have we don't have parts where it narrows, it's just a straight tube. Even then, we still have formants. We still have these spaces that resonate at their own frequency. We still have it, even without those narrowings. And that will produce, like we mentioned last time, a schwa. Basically, that produces a schwa. 都很均匀，它自己分配. And we're getting these several pitches at the same time. So 我们还是几个 formants 同时会听到它的那个 resonating frequency. Okay? And then, furthermore, these resonance frequencies change in predictable ways when the tube is squeezed at various locations. If we add those narrowed parts of the tube, then we know that it will change in certain ways, 而且是可以预测得到，因为是有规矩的。我们知道这个东西是有一个什么 rule governing it. Okay? This means that we can model the acoustics of vowels in terms of perturbations of the uniform tube. That means we can put those little dents in the tube and then figure out the frequencies based on what we know about these rules, how this works, how the resonances work. Okay? For example, when the lips are rounded, that's adding a narrower neck in one part of the tube. Is that right? You have to kind of look at me because I'm pointing to what I'm talking about. So if we just have a straight tube, but here we have a narrowing at the lips if we have more lip rounding. Lip rounding makes the opening smaller. What does that do? For example, when the lips are rounded, the diameter of the vocal tract is smaller at the lips than at other locations of the vocal tract. That part's clear now? Okay, 其他的都比较粗，可是这里变得比较细，因为那个嘴唇有 rounding. So we can predict the form and frequency differences between rounded and unrounded vowels. So if we know about lip rounding, then we know that the formants are going to change. In fact, it's going to lower a formant. And which formant does it lower? F3. Remember, F3 is the one where we didn't have a really clear place that we could point to. F1 is close to the vocal folds. F2 is close to the lips, right inside the lips. F3 involves lip rounding. Because the lips round, that's going to lower the frequency of F3. F3 is influenced by lip rounding. And this is giving you a slightly more technical physical explanation about why that happens. Because in the tube, if we know the narrowing, we can predict how that resonance frequency is going to behave. In this case, it's going to go down. We know that. So that means the first paragraph should now be clear. 厉害，很棒. You're really good. Okay, next.
Here's how perturbation theory works. For each formant, there are locations in the vocal tract where constriction will cause the formant frequency to rise.
The formant frequency.
The formant frequency to rise, and locations where constriction will cause the frequency to fall.
All right, this is important because this is giving us a new idea. From the first paragraph, we only learned that a constriction is causing a lowering of one of the formants. However, it depends on where in the vocal tract the constriction occurs. If it's at the lips, it will lower the formant. But if it's at some other place, it may actually raise the formant frequency. So it doesn't have to go down. It depends on what point in the sound wave it is located, at what point it's located. Let's keep going.
Figure 8.2 shows these locations for F1, F2, and F3. In this figure,
because figure is repeated. In this figure,
the vocal tract is pictured 3 times.
3 times.
3 times, once for each formant, and is presented as represented as a tube that has the same diameter for its whole length. Length.
Put a K in there.
Length.
There we go.
And is closed at the glottis and open at the lips.
Right.
This is approximately the shape of the vocal tract.
Pause. The shape of the vocal tract.
This is approximately the shape of the vocal tract during the vowel
Very good. Did you understand that? We've got figures at the bottom of the page. F1, F2, F3. And this shows where we have, this is called maxima. Actually, they're going to explain it in the next paragraph, so I won't go into too much detail about it. But you can see they're only marking 2 things. For F1, it's P, which means pressure, and V, which means velocity. And then you've got 2 more marked in F2, and then you've got still 2 more marked in F3. In any case, we're going to get more explanation in the next paragraph, so let's continue.
The letters P and V
in the Foreman 1 to Foreman 3 tubes indicate the location of pressure maxima, P, and velocity maxima,
And velocity maxima.
V. In the resonant waves,
Hmm?
in the resonant waves
That's better.
that are bouncing back and forth between the
They are
lips,
bouncing back and forth. Okay, what you're doing, what you did the first time is that are bouncing back and forth. 不是这样子. We're just keeping on going, and each one has about the same level of stress. That are bouncing back and forth. That's a tonic.
that are bouncing back and forth,
Back 不要太高.
back and forth
There we go.
between the lips and glottis during a vowel.
During.
During
Good.
a vowel.
Okay, do we understand this so far? First of all, say F1 to F3. It's form at 1 to form in 3. That's the long form, but we usually just say F1 to F3. Then we have maxima, we have pressure maxima and velocity maxima. That means the part of the wave. I think I'm going to need to put a figure on the screen. That means the part of the wave where the sound is moving the fastest, where the pressure is the highest or the lowest. The speed is the highest or the pressure is the highest. It's two different things here that we're going to see in the wave. Now, we're talking about pressure maxima and velocity maxima. If we are already at the maximum point that the wave is going to go, this is a maximum, right? This is the maximum. When it goes all the way here, that's as far as it's going to go, and then it's going to turn back. So at this point, it's a pressure maximum. Okay, that's a pressure maximum or maxima. That's a pressure maxima. That means the pressure is as strong as it's going to get, and after that, the pressure is going to get weaker. And where do you think it's fastest? Where do you think the wave is moving fastest? Velocity is speed. Is it going to be fastest here, or is it going to be fastest here? Think a minute. Just use your brain. Imagine something making this trail in space. We know that the pressure is at its maximum here. That's a pressure maximum, right? But how about speed? Because the wave is moving forward, actually. So where do you think it's the fastest? Think about trying to ride your bike over a hill. It's pushing here, and it's suddenly run out of push, so it's just going to drop back. But here, it's got a lot of energy to push all the way up again. So it's going to be fastest where? At the node, right? This is a velocity maxima, and this is a pressure maxima. And these will hit 固定的 places in your vocal tract. 它会有固定的地方会碰到. And remember, this is called a node, and the pressure maxima is called the antinode, the tallest part that goes up and down. That's the pressure maxima, that's the antinode. Where it doesn't seem to be moving in the middle, that's the node. The node is the velocity maxima. That's where it's moving the fastest. And then once you understand that, this should be easier to understand. Okay? Now, I'm going to turn it off since you've seen it, and it's kind of bright. So, if you have a constriction in certain places, the Foreman frequency will rise, and in others, the frequency will fall. And here, the letters P and V, let's see, how far have we read? The first sentence? During the vowel. During the vowel, okay, during a vowel, the first sentence. All right, so P stands for pressure, that's a pressure maxima. V stands for velocity maxima, that's where the speed is the fastest. And you can see where it hits in the vocal tract. 下面就是a model of the vocal tract, those three figures. And the pressure is highest where? In the first one, in V1, in F1. At the glottis, we've got a pressure node. That means it's already 已经到顶了，现在要走回头路了. So you can draw a little pencil line from either the top or the bottom because it's going to reach all the way to the other end. Then it goes up and down, and V, the line is going to be right in the middle, right between the upper and the lower edges. It's going to be right in the middle because that's the node. That's where it's going to be turning back. It's gaining speed to make another bump. Are we all clear? Everybody 可以吗? Yeah? Annie 也可以吗? All right, good. Just say so. Well, in my drawing, I've started the pressure wave at the bottom. 这个角从左下角我就开始画。那个是已经到顶了，那个 pressure wave 没有办法再大，它现在要走回头路了。So it goes up, makes a pressure, it has another pressure maxima here, goes down, another pressure maxima here. It ends up right in the middle. 如果是中间画一条线，那个就是 node 的所在地，对不对？因为它中间会交叉的那个地方，就是在中间。所以这个 wave 的终点就是刚好在中间。And that's a velocity wave. 就在那个中间那个 node， 它就会加快。在 pressure maxima， 它会慢一点，才会慢慢滚下来。That's all clear? Vivian? Not quite so clear? Okay. Again, remember in the picture of the wave goes up and down and up and down. When it goes all the way up, it's run out of pressure. 已经到顶了，它的压力已经到最大了。That means it has to go down again. But actually, it's going like this. So it gets up to here, 那力气已经用完了, so it's going down. When it gets to the middle, 就是那个中间那条线, that's the node. When it gets to the node, 速度就会加快, because it's has the most energy to produce that next 鼓出来的地方。然后呢，它又到顶了, ran out of the energy. 它又往上了. Gets up to here, and then it gets its energy again, pushes up, 到顶了. So it's at the nodes that the speed is the fastest. That's where the speed is the fastest. 然后 vocal track 里面有固定的 pressure maxima 和 velocity maxima 的点，它固定的。所以看你在哪个地方缩小它的直径，会有不同的效果。你会影响到它在最快的时候，或是在压力最大的时候。压力最大的时候是比较慢，速度最快的时候是压力比较小。所以你看你压到哪里，就会影响或者速度或者压力，对不对？So, the letters P and V in the F1 to F3 tubes indicate the location of pressure maxima and velocity maxima. So they tell you 那个 wave 到底是到顶了吗？还是停留在中间，准备那个冲刺了？ So if you see a V, your line's going to be right in the middle. The wave is going to be stopping right in the middle. Not really stopping, but that's where it is. Wherever you see a P, it's either way at the bottom or way at the top. Okay? So depending on what part of the vocal tract we narrow, 我们就压小它的哪个地方，就会有不同的影响，可能会影响它的压力，也可能会影响它的速度。影响压力跟影响速度对频率的效果不一样。如果刚好是在 velocity 那个地方，那是 lips。那 lips narrow 的话，我们刚刚说 F3 会有什么结果？会在 F3 上面发生什么作用 ？Right. The frequency is going to go down if we have a narrowing at the lips, which is a V point, velocity. 那是刚好停留在中间那个地方。So if we narrow the vocal tract at a V, the frequency of that formant is going to go, that resonance is going to go down. So that 我们就可以那个推理出来 if we narrow it at a P point, what will happen? 它的速度已经是最慢的 ，pressure 已经冲到最大，可是我们去压那个地方，等于是我们把它的 pressure 压到别的地方去，所以 we can guess that the resonance frequency is going to go up. Someone got it. So just reverse what we did at V. At V, we're right in the middle. We're at the fastest part with the lowest pressure. If we narrow it, the frequency of the resonance goes down. But if we narrow the vocal tract at a point marked P, 它的 pressure 是最大的， 速度最慢的. But if we push on it, it's like we're sort of pushing harder. We're narrowing it at that point. The frequency is going to go up. 就是刚好相反的一个效果. That's tough stuff because this is physics, but it's actually totally conceptual. You can just picture it in your head and try to work it out. Because if you get V, just reverse it for P. We're going to squeeze it at P, and that means the frequency is going to go up. Okay? So it depends on what part of the vocal tract we have a narrowing. If it happens to be on a place marked V, 就是中间那个 node 的地方, our resonance frequency is going to go down. If it happens to be at a point where the wave is already at its maximum, it's already hit one of the edges, it's going to squeeze that, it's going to squeeze the frequency up. Okay? Let's see if we can follow that. So read the first sentence of paragraph 3 again, and we'll see if we can get through the whole paragraph and get everything. 好，再来一次.
The letters P and V in the F1 to F3 in the F1 to F3 tubes indicate the location of pressure maxima P and velocity maxima V in the resonant waves.
Resonant, watch the stop.
In the resonant waves.
Resonant, wait, in the resonant waves.
In the resonant waves.
Your T is still not clear enough. You're going resonant waves.
Resonant.
There we
in
go.
the resonant waves.
There we go.
That are bouncing back and forth between the lips and the glottis. Between the lips and glottis during the vowel.
All right, and remember that glottis is marked what? P or V? P, okay, that's a pressure maxima, and the lips are marked V, which is a velocity maxima. Keep going.
The fact that 3 resonant waves can be
watch that. Stop it. Resonant.
resonant waves that can be present in the in the vocal tract at the same time.
Watch your T's. At the same.
At the same time, it's difficult to appreciate, but true.
So he admits this is a little hard. You can feel better. 有点难. He says this is kind of new. We haven't thought about that before, but that's the way it works. Keep going.
The perturbation theory says that if there is a constriction at a velocity maxima,
at a velocity maximum.
At a velocity maximum.
Okay, the singular should be maximum. I was hesitating because he kept using maxima everywhere, but that's actually the plural. Maxima is the plural. Maximum is the singular. So I'll go back to that usage. Go ahead.
In a resonant wave, then the frequency of that resonance.
In the resonant wave, actually there should be a comma, but we don't like to put 2 commas so close together. We leave one out, but actually we need one before then. So. Yeah, go ahead.
In a resonant wave, then
right.
The frequency of that resonance will decrease, and if there's a constriction at a point of maximum pressure is right because we repeat it. Maximum pressure P. Then the frequency of the resonance will increase.
Okay, increase.
Increase.
Okay, that's common in Taiwan. I don't know why. Increase. You make it too long, then the S sounds like a Z. There's no Z. It's voiceless, so E is a little bit short. Increase. Everyone, increase. Release. Decrease. Okay. All right, I want us to go over that paragraph. Everybody read it silently. Put together with the explanation I just gave you. It should be basically restating what I just said, or I was restating what it said. So read it over to yourself and then look up when you're ready. Anybody not ready? Raise your hand. If you're not ready. All right, it's clear? So you just need to remember that if it's marked P, then if we restrict that area, if we restrict that point at P, then if we make the opening, if we make the passageway narrower at a point marked P, then the frequency will go up, right? At V, it will go down. That's what we need to remember. And it's just the shape of the wave where it happens to fall in the vocal tract. These are the 3 formants. They're going on all at the same time. 同时都在进行. Even when we don't have any special constrictions. For everybody say Do you feel any constriction in your vocal tract? This is what the sound you make when you fa dai, right? You're staring in his face. 这是发呆的声音. That's That means that we are not using any muscle effort. If we're not using any muscle effort, we're not really constricting anything in particular. Even with that relatively neutral configuration of our vocal tract, we're going to get a vowel, we're going to get constrictions. We've got 3 formants going at the same time. Each one has a different way for the wave to fit into the vocal tract. It's going to have different V's and P's marked, okay? And so depending on where we restrict or constrict the vocal tract, we're going to get either an increase in frequency of that resonance, either F1, 2, or 3, or if we constrict it at a different point, namely V, then we're going to get a decrease. Okay, we've gone over that several times. 希望没有不耐烦. That's how it works, so it should be clear enough. Let's try the next paragraph.
Given these simple rules for how resonant frequency changes when the shape of the resonator changes.
Okay, and here we wouldn't stress the last 2 words because we were repeating them. What's new? When the
Shape.
Go ahead.
When the shape of the resonator changes.
Right. Changes. Right.
Consider how to change the F1 frequency in vowels. Constriction near the glottis, as found in low vowels, is closer to a pressure maximum than a velocity maximum.
Velocity maximum.
To a pressure maximum than to a velocity maximum.
V.
V.
We should read the letters so
okay.
we remember because we have to mark them.
Okay. So the F1 frequency will be
It
high.
would be V, F1.
V.
Why is it V? F is a consonant. F starts with a vowel, right?
Okay. So the F1 frequency will be higher in low vowels than in schwa.
All right, let's concentrate and see if we get that. Because the glottis is marked P, and if we constrict our vocal tract near the glottis, and that's what we do for low vowels like ah, ah. Can you feel constriction way down there? Ah, ah. You've got a constriction way down there. We're constricting our vocal tract near that P point. So therefore, what's going to happen to F1? Because remember, F1 is that format that's close to the vocal folds. We're constricting the vocal tract near a P point for a back vowel, for a low vowel. Ah. So that's going to do what to the F1 frequency? Remember, if we narrow the diameter at a P point, it's going to do what to the resonant frequency? It's going to go up. So that means that F1 will be higher for a low vowel than for, what are we comparing it to? Schwa, right. For schwa, it has 1 frequency. But because we're constricting our vocal tract at a P point to make a low vowel, ah, we're going to be squeezing at a P point. That's going to raise the frequency of F1. Now it's starting to make sense. We're making it more concrete. This is heavy stuff. I mean, it's really, really cool. If you know this stuff, this is new this year. We didn't have this last year, this section called Perturbation Theory. We didn't have it before this year. This is pretty interesting stuff. So we're okay up to the word schwa, right? Let's go on.
Constriction near the lips, as found in high vowels and round vowels, is closer to a velocity maximum, so the F1 frequency will be lower in high vowels than in schwa.
Right. So we're going to have a constriction way towards the front, like for E, we've got that 舌头翘起来的地方是很靠近嘴巴外面，对不对? So it's very close to a what point? Where the lips, which is a velocity point. There we go. So we know that the frequency of that resonance is going to go down. Okay, so there's a physical explanation for everything that happens in speech. Okay, so that makes 2 things pretty clear, I hope. If we have a low vowel, we've got a constriction near a P point, it's going to raise the F1 frequency. If we have a constriction near the lips, like we do for high vowels, it's going to, what? the F1 frequency will be lower in high vowels than in the schwa. So we're going to lower that F1. We're talking about F1 now. Okay, go on.
The rules apply in the same way to change the frequency of F2 and F3.
All right, so the same thing is going to work for the other resonances, for the other formants as well. If you constrict at a P point, it raises the frequency. If you constrict at a V point, it's going to lower the frequency. So I think that should take care of it. Let's keep going.
For example, there are two ways to raise the frequency of F2. One involves a very different constriction.
A very what?
A very difficult constriction near the glottis.
All right, let's just start there. We want to raise the frequency of F2. F2 also has a P point at the glottis. All of them do. So in order to raise the frequency of F2, one way we could do it is to constrict our throat. 就是喉咙比较深的地方，我们可以让它紧。When we're saying E, we can raise it. We can raise the frequency by going E if we constrict it down here. But it's hard. It's hard, right? It's hard to do that because it takes a kind of strain that is not natural if we want to just raise the frequency of F2. So because it's harder, and not because, but it's harder to do that, we're going to look at something else. Go ahead.
But without tone root constriction, which is near the first V in the F2 resonance wave.
That's right. So we have to constrict the glottis, but we can't use tongue root constriction. 就是舌根很深的地方不能用到那个地方，因为它很靠近一个什么？我们要喉咙把它弄紧，我们就可以 raise F2。可是那是很难做到的，而且同时不能用一种方式来 constrict 那个地方，不能用舌根深处，因为舌根深处比较靠近哪里？ Velocity, 它靠近一个 V 的点。So if we use that method, instead of raising the frequency, we're going to, if we constrict our tongue root, which is close to a velocity point, if we use that method, what's going to happen? It's going to lower the frequency. So it's really hard to control things down here. To use this particular kind of constriction to raise the frequency of F2, 那就很难. Okay, keep going.
The other involves constriction with the tongue against the roof of the mouth. This is the most common maneuver used to raise the F2 frequency.
So to get that high F2 that we need for E, we're using our tongue, getting really close to the front of our mouth. E. Now that's right at what point? Right, but in terms of V and P. It's close to a pressure point, so if we constrict there, it's going to raise the frequency. E, E, you can hear it getting higher. E, tried it. Start from a lower point and move up to an E and you'll hear the frequency going up. It's getting higher and higher. We're at a P point. So more constriction is making a higher frequency. However, we remember that the lips are a V point, so E is going down. E is going to put F2 down. Okay? That was hard stuff and we got through it. Is it all clear? Sylvia, is it okay? Not okay with anybody? Please be brave and tell me if there's anything that I can try and make clearer. Anybody? We're okay? Annie okay? That means we've earned a break. Okay. Let's continue. We have a new section now.
Acoustic analysis. Phonetic scientists like to describe vowels in terms of numbers. It is possible to analyze sounds so that we can measure the actual frequencies of the formats. It's a schwa. We can then represent them graphically as in figure.
Graphically, don't pronounce the last A. Graphically. And that's true for almost all ALLY adverbs. 那个 ALLY 的 A 就不要发音. Graphically.
As in figure 8.3. This figure gives gives the average of a number of authorities' values of the frequencies of the first three formats in 8 American English vowels. Try to see how your own vowels compare with these.
All right, I want you to look at this figure now. Let's just go over what we just read. We can describe vowels by giving the center frequency of each formant. We all understand that now, right? Each formant, 它不是那个黑黑的、粗粗的一条吗？ It has a center frequency. 我们就用那个作为我们的 number， 我们就取这个数字当一个数据。So we'll pick the center frequency of F1, F2, and F3. We put those numbers in this table, and then we get E. That's a way to describe E. So we understand 8.3 then? The formant frequencies are different for I because, for example, F2 is getting lower for I. Right? E, F2 is really high. I. We can hear the frequency going down, and look, the number's lower. And for I, F3 is also going down. And F1 is going up. F1 is steadily going up as F2 is going down as we go through E, I, A. Okay? These are just numbers that mark in a more compact form the information that we have on the next page. So if you turn over to page 194 at the bottom, those are the spectrograms that actually record and represent the formants in graphic form. And we just picked the middle frequencies of those to make figure 8.3. So now these spectrograms sort of make sense, right? So starting from the bottom, F1, F2, F3. You can also see F4 and other formants, but we're not going to bother with those. We're just going to focus on F1, 2, and 3. And you'll see a voice bar throughout all of them. 下面那个灰灰的一条就是 voicing, 表示有 voicing. And continue.
Do you have a much larger jump in
Larger?
larger? Do you have a much larger jump in the frequencies of the second format, which you hear formant
Yeah.
of the second formant, which you hear when whispering between and a, as compared with e and I and a?
Right.
Do you distinguish between hard and hard in terms of their format frequencies?
In terms of their,
Formant frequency.
right? Okay, format, remember it's a schwa in the second syllable. All right, let's try that. We're going to measure the jump between two pairs of vowels. We're going to go from e to a, which are notoriously difficult for Taiwanese. E and a, bet and bat. A lot of people cannot tell the difference, right? Bet and bat. So let's whisper e and a. Whisper to yourself and listen to the pitch change. And then whisper from I to e. And compare the two and try to decide which one has a bigger jump. Which two vowels are more different from each other? Is it I and e, or is it e and a? Now, just judging from 质感, as a Taiwanese, you'll probably say which two are closer. E and a, because they get confused in Taiwan English all the time. So we're guessing that e and a are closer to each other than I and e. So whisper to yourself and try not to be bothered by the people around you. But whisper these two pairs to yourself and then tell me which one you think has a bigger jump. Okay, go ahead. Okay, what's your conclusion? Which one has a bigger jump? E and a? You think and A have a bigger jump? For F2 anyway, right? Okay, let's compare. That's interesting, especially after what we were predicting. And then how about for had and hod? Can you hear different frequencies? Yeah, they're quite different for us because in Taiwan we still distinguish them. In America, a lot of people don't. Even in pronunciation training software, many people now want you to pick ah when you hear ah. I protested against that. I said, you know, when I hear ah, it's not an ah. He said, I want to only teach the things that are absolutely necessary to comprehension. And you can say that if you belong to a dialect group that does not distinguish between ah and ah. 对他来说，这两个无所谓。可是 for me 有所谓啊。And so you're not teaching ah anymore. 我就觉得，我听到 ah 我怎么样不会选 ah. But as somebody who does not distinguish between the two, it doesn't bother him at all. And he thinks, 这样就把整个系统简化了, it's better for the students. Wendy says, no. Why not? Half the people already do not distinguish between the two in America. There still have to do. That's what I told him. I said there's still half of us that do distinguish.
Know what they are talking about.
Because it helps you distinguish more sounds. Because a lot of people still do had, hod, tot, taught. So it still helps you. And for a foreigner, it's hard enough already to understand another language. And if you lose a distinction, that probably makes it even harder. That's sort of what you're saying? Okay, anybody else have any thoughts? When we're designing pronunciation, teaching software, he's trying to get people to recognize vowels better. Foreigners, non-English native speakers. So, ah and ah, 合并为 ah. Vivian, you reacted a bit.
I think even you don't distinguish them, but still there are some people distinguish them, and you have to hear their sound, so you'll know they are two different.
So it's like you're missing a piece of your tools in your training if you think everything is okay as ah. So you think that it's better to have the training than not, because it's always an extra help when you need it. Okay, anybody else? Funny that you all support my point of view, isn't it? Okay, okay. Anybody else have any thoughts? It's hard to be really objective, because I've been giving you a lot of propaganda saying ah and ah are important. If you had a different teacher who doesn't distinguish them, you might feel differently. Okay? I don't like it, but maybe some people will think it's fine. All right, so we're okay on this. Let's keep going.
There are computer programs that can analyze sounds and show their components. The display produced is called a spectrogram.
Right, in Chinese, 声谱仪 is the device. It's called a 声谱仪, is a spectrograph. And a spectrogram is, they have different names for it, but you can just call it 声谱. That's one way to call it.
We have seen spectrograms in prior chapters without much discussion of how to interpret them. Now is a time for a little more detail.
Now is the time.
Now is the time for a little more detail.
Now is a time and now is the time give us a different feeling. Now is the time means now is okay, but maybe another time would be okay too. But if it's now is the time means get on it now. 不要再拖了. That's what that means. Now is the time to blah, blah, blah.
In spectrograms, time runs from left to right. The frequency of the components.
Once more, frequency.
The frequency
Good.
of the components is shown on the vertical scale, and the intensity of each component is shown by the degree of darkness.
Good. All right. How many dimensions do we have in a spectrogram? They also call them 声纹 sometimes. It's an analogy with 指纹. But please don't think that everybody has a unique spectrogram and we can use it to identify a criminal the way we can with fingerprints. So 声纹 is kind of misleading. 声谱 is good enough. Okay, but 声纹 is one other term that you'll hear. How many dimensions do we have on a spectrogram? Okay, why 3? I'm not saying yes, so why is it 3? Louder?
Just thinking about
Formants, okay. Your answer is right, but the reason is not right. Okay? That's right. Okay, explain, Sylvie.
Because the first dimension is horizontal, the time.
All right, so let's go slow. The first dimension is the horizontal one, and it measures time. Time is just ticking away here, and we see that in the horizontal dimension. And as I mentioned in a previous class, these are broadband spectrograms, so that means that each pulse is very clear. The time is resolved very clearly. It has high resolution for time, 可以这么说。它时间的这个参数上，它解析度很高。Okay, and?
Second dimension is a vertical for frequency.
That's right. So the vertical dimension shows us the frequency, where we have some kind of a sound, a resonance, or whatever. That's going to show up on the vertical scale. That's dimension 2. And we have?
Darkness, so like this, so it's the third dimension.
That's right. 深浅,颜色的深浅 gives us our third dimension. And that tells us how loud it is. That's amplitude. Okay? So these are three-dimensional even though we can see them on a flat piece of paper. Let's go on.
It is thus a display that shows, roughly speaking, stark bands for concentrations of energy at particular frequencies, showing the source and filter characteristics of speech. There are several.
Let's skip that. 因为那个是做广告. Okay, the rest of it is just stuff about the tools. So it says if your computer has a built-in microphone, try recording your pronunciation of heed, hid, head, had, and making spectrograms of them. You've already made waveforms of these, remember? So we already are familiar with this. It's because they introduced it early, so we needed a tool to see them, see them early. And you can do it if you're in a hurry, very simply, with WASP, because they have 4 things that you can see. You can see a broadband spectrogram, you can see a narrowband spectrogram, you can see a waveform, and you can see a so-called pitch track. It will analyze the fundamental frequency in the vertical dimension. We can see the fundamental frequency in the horizontal dimension in what way? Okay, think about this and you'll understand spectrograms better and better. We can see the fundamental frequency in the horizontal dimension in what way? We can just cut off a piece that's 1 second long, right? And what could we do? You notice it has very fine vertical lines, right? Each fine vertical line is what? 1 pulse of the vocal folds vibration. So if we cut off a piece that's exactly 1 second long, what can we do? You can count how many pulses there are, and then you get the fundamental frequency, or F0. So you can actually get a fundamental frequency from the horizontal dimension because it's time. How many pulses are pulsating over time? Okay? And in the vertical dimension, we're going to see at what frequency. That measures frequency again. But in this time, it's spread out over a numbered line. It will show where the frequencies fall. It's very tedious to count those little pulses at the bottom. So we're going to spread them out. And also, they're only going to give us 1 frequency if we count it that way. We'll only get F0. We're not going to get F1, 2, and 3. This is only giving us F0. If we count those pulses, we only get F0. When we go to the vertical dimension, we also get F0, the voice bar at the bottom, 就是灰灰的，总是有一条在最下面的部分. Remember the voice bar? That shows there is voicing. 当有 voicing 的时候, we will have a voice bar. And that will give us the 区域 of the frequency, but not very precisely. Okay? After that, we're going to, because it's a broadband spectrogram, 它的那个frequency dimension 是蛮模糊的. 它时间解析度很好，可是 frequency 会很模糊，很 blurry. So it's going to give us the general areas. We've got a general area, just a very general area for the voice bar. 是就是蛮泛的，蛮 general. Then for F1, F2, and F3, F1 here and F2 and F3, we're going to have a band where the formant is. 那个也是蛮模糊的. If we go to the middle frequency, then we'll get something we can use, a number we can use. 可是那个 band 很宽，因为它把很多的 frequency 都模糊在一起，为了是要那个时间很清晰，我们不可能这个很清晰，同时那个很清晰是做不到。We'll talk about that in more detail when we get to talking about narrowband frequencies. But remember, there's always a trade-off. And this is not a matter of 科技还不够发达. That's not the problem. The problem is, if we make this very clear, this is going to be blurry. 就是天经地义的事. If we make the overtones really, really clear, that makes the frequencies really clear. 时间就会模糊在一起. So that's something you'll need. It's probably going to be on a test. So make sure you put that in your notes. Suddenly the pens get picked up. Okay, let's go on.
Figure 8.
Figure.
Figure.
Not figure.
Figure.
There we go.
8.4 is a set of spectrograms of an American English speaker.
An American English speaker.
An American English speaker.
Listen. American English speaker.
American English speaker.
Right.
Saying the words hid, head, had, hot, hood.
Let's practice those just to make sure that we've got our vowels right on target. Everyone, heed, hid, head. Okay, make sure if you're having trouble with use your hand to push your jaw up. Head, had, hod, hood, hood. Do you know what they all mean? Do you know what a hod is? Do you remember? 是个油饼，然后上面有一个好像一个角落的一个形状，可以搬砖头用的。That's a hod. 这是现在比较少看到的。I'm sorry, I'm going to have to. Next time we're online, I'll show you. But it's got a long handle, and it's sort of like a pocket made of metal, and then you can stack bricks in there. 是搬砖头用的一个工具。You don't see those too often these days. Hod, that's the past tense of hem and haw. 就吞吞吐吐的讲话 is to hem and haw. Well, he said that's to hem and haw. He hawed. 然后 ed 去掉 haw is part of hawthorn, 就是山楂. Just so you know, because we see these words all the time. So you should know what they mean. Let's continue.
Because the higher frequencies of the human voice
Watch the N.
Human
Right.
voice have less energy. The higher frequencies have been given added emphasis. If they had not been boosted in this way, the higher formants would not have been visible.
All right, stop there. This is a technical issue. In these pictures, everything looks very dark and clear. However, in the vocal tract, among F1, 2, and 3, which one do you think is going to have the most energy? Think a minute. It's in vowels and consonants. You've probably read it already. If you haven't already, it's coming. Of F1, F2, and F3, which one do you think has the most energy? Good. Why?
I'm thinking about the shape that each format will decrease.
That's true? Can you give a physical reason for it? Just think, you can figure it out. Think of where F formant is centered. Amy? Not quite. What is our energy source? It's air popping up through the vocal folds. So, can you take it from there? If you have an air gun, is the pressure going to be higher close to the gun or further away from the gun? Right. Does that explain it? So this is your air gun. It's going to be, we're going to have more energy down here, and it starts getting 比较散 when it comes up. So I believe it's 40% of the energy is concentrated in F1. I believe it's 40%. That's what I remember from vowels and consonants. And so that means that the lowest frequency is going to be the darkest. And what's going to happen to the others? They're going to get very 淡，那个颜色深浅会变得非常的浅，看不清楚。So 动了一点手脚，他们调整了那个深浅的那个程度，就是让它变黑了。Higher formants 大概是从 F2 开始，就是加了一点那个颜色加深了。Otherwise we couldn't see it. So when you see stuff like this, you make sure you understand what's going on. 因为这个是不是天然的一个 if there can be such thing 天然的 spectrogram， 这是动了手脚的。Okay? Okay.
The time scale along the bottom of the picture shows intervals of 100 milliseconds.
100 milliseconds.
100 milliseconds. So you can see that these words differ in length.
All right, let's understand that. Look at the vowels that are displayed in 8.4 on 194 at the bottom. 它的那个宽度都一样宽吗？ Which one has the longest spectrogram? Which one has the longest? Which one is the widest? Let's put it that way. Which one is the widest? Ah, right. And this is American English, remember. If it were British English, it would be probably quite different. But ah, it's a long diphthong, basically. Ah, hod. It's quite long, and this is proof. What's another long one? Pretty long one. Ah is pretty long. Is pretty long. Is supposed to be a short vowel, but remember, in American English, some of the short vowels have gotten quite long, especially A. A has become longer in American English than it is in British English. It's a short vowel because we can't use it in an open syllable at the end of a word, but it's still quite long. And then, what else is pretty long? E is pretty long, then U, and then we're going down to the shortest. And then the very shortest is I. Now remember, I've told you in American English there are only 4 really short vowels. What are they? I, E, A, and schwa. I, E, A, 到 V. I, 到 3, 到 V, and schwa. 这4个. Those are the only very short vowels in American English. All the other so-called short vowels are not hugely short. Is not so short because it's actually a bit of a diphthong. Remember, short vowels in American English, they have a little tail, which is a what? If we didn't mention it before, I'm mentioning it now. I can't remember if I told you before. That's the biggest difference between short vowels in American English and in British English. In British English, short vowels are just pure vowels. One pure vowel. But in American English, every short vowel has a little schwa at the tail. So for American English, I say good, good. Can you hear the schwa? Good. In British, it's good, good. That's good, good. Can you hear a schwa there? If you hear a schwa, I'm saying it wrong. That's one of the first things that I was told I was doing wrong when I was trying to learn British. He kept saying I sounded so American. He says, you're putting a schwa there. That's the problem. And it was hard to get rid of that schwa because it's one of those things we do without thinking. Just like 万一那个 n disappears, 你们没有感觉。那个 schwa 我们没什么特别的感觉. It's just there. We're so in the habit. So is a bit of a diphthong. It has an off glide of a schwa. All of the short vowels do in American English, but the shorter short vowels have less of a glide. So especially for sit, 那个 schwa 的那个 glide 很小很短. Bed is also quite short. But for 它还蛮明显. Okay? And sad, you can hear it in that. Sad is 本身就比较长. So when you see the formants changing, right? The formants 有变化，那个就是那个 schwa 的那个尾巴. Okay? And 本身也是 diphthongal. Is a long vowel, not a short vowel, but it's also quite diphthongal. So are we clear so far? Good, let's keep going.
The words were actually said one after another, but they have been put in separate frames
In separate frames.
separate frames as
Once more, not frames, frames.
frames, as there was no point in showing the blank spaces between them.
Between them, right. So they put them in the words, I believe. Yeah, it's he'd, hid, head, etc. They cut out the vowels, and they just cut out the times between them, and cut out the spaces. So they put them in different frames. So 每个有独立的图片. Okay.
The vertical scale goes up to 4,000 Hz, which is sufficient to show the component frequencies of vowels.
Now that sounds like a really boring sentence, doesn't it? When you go to papers, sometimes paper presentations, or if you read journal articles, sometimes in phonetics, they give you long descriptions of, well, I used this certain this certain recorder, and then I used this kind of a program to analyze the data, and then I used blah, blah, blah. 都是过程，它在形容过程一大堆. And that's usually the part that we would like to skip over. However, this is significant. It goes up to 4,000 Hertz. That's enough to give us the information we need for vowels. This is significant. Let's look at other spectrograms that we have. We need to find one that is not for vowels, that's for consonants. Let's go ahead a bit. Let's look at page 202. In this part, we're talking about consonants. Look at the scale there. What kind of a scale do we have here for the spectrogram? Goes up to 8,000. Now, what's the reason for that? Shh, exactly. We've got high frequencies and fricatives, don't we? And we need a larger scale. We need a larger range of frequencies to show some of those. And we can't even show all of them because some of the frequencies go up to 12,000 and above. 14 is possible. But we need to see at least up to 8,000 to show consonants. But for vowels, do we need that? No, because everything is voiced. The resonances are voiced sounds. The voiced sounds that are not fricatives, that are not friction, things like that, they're going to be mostly below 4,000, at least up to F3. There are more formants above F3 that will go higher, but we don't need those. So that sentence was significant. How about if we just finish the paragraph?
Because the formants have greater relative intensity shown by the darkness of the image, the image,
Right.
they can be seen as dark horizontal bars. The locations of the first three formants in each vowel are indicated by arrows.
That's right. So if you're still not sure exactly where the formants are, look to the left. You'll see 1, 2, and 3. The arrows are pointing at exactly the middle, pretty much the middle frequency of each of the first three formants. So you can find them easily on the spectrograms. All right, we covered a lot of solid stuff today. 非常的扎实. Okay, you should feel 成就感. Getting through this stuff, especially that new section that we didn't have other years. The tube models and the perturbation theory are both new this year. The length of the book hasn't really increased, so he probably cut some other things out. Review and preview, it will really help you. We're going to be working very intensively on spectrograms pretty much for the rest of the chapter. So you're going to need to understand what's going on, and we'll be doing more spectrogram work ourselves at home with your computer. And I also asked you to do a web page. What was it? Page 11, and it will give you a link to the online tutorial on logarithms. The next page will give you, I said it was one paragraph that was taken out. It was actually two, I just checked. The two paragraphs that were omitted from this chapter in previous editions, I've got them on page 12. If you're curious, 它到底删除了什么? We always like to know what's missing, what's hidden, right? Well, the hidden paragraphs are preserved on page 12. Okay, so I think we're set for Wednesday. Don't forget your vowels and consonants. We'll see you then.